And this is sort of a typical view of our sites in the middle of June. No, that's more like February, but note that there's a lot of opportunity for sublimation from these systems, especially from the capture of snow in the canopies, which can lead to quite a bit of sublimation loss. So there's another factor. If all the snow is lost from the canopy, signal's not getting down into the snowpack, which most people measure and which also contributes to the runoff. So it's another factor we're looking at. One thing that we're interested in is this large-scale mortality effects of the bark beetle epidemic in North America. And there are pine beetles, there are spruce beetles, there are a variety of beetle species that are attacking different species of conifers, pines and spruce in the North American conifer systems. And you can see the effects that it has on the forest structure. These are red trees that have been attacked, and those are trees that have been recently attacked. The leaves have died, and so the leaves are still hanging on the trees. But within a year, all the leaves drop off of those trees, and they turn into just gray skeletons. And of course, that's going to have a large impact on the water balance and energy balance of the surface, which might then lead to some isotope effects that can be recorded in the snowpack. And indeed, this paper by Biederman et al. That looked at a pine forest in, you were on this paper, right? Yeah, this is at the Chimney Park site, lodgepole pine, showed a really nice potential effect of bark beetle mortality on sublimation being recorded as a change in the water ice, in the slope of the water line in impacted areas when you compare it to non-beetle infected areas. And so here's a case where the snowpack is recording some effect of this sublimation fractionation, which has a kinetic isotope effect. It's being recorded here. But sites are different. We did a lot of measurements of snow around the basin and also around our Ameriflex eddy covariance site in the high elevation subalpine zones with spruce and fir to look for this mortality effect and its influence on snowpack metamorphosis. And this goes right to your points about how moisture is ablated, snowpack is ablated from the system. And these are data from our high elevation zone, quite a bit higher than the study from Biederman that Elise worked on. And what the figure I'll show you the one on the right first. This is the profile of the snow, but it's normalized for the water content of the snow, but you can think of that as its depth, okay? And then the relative local the offset from the relative local meteoric water line on the bottom. And so I know the units are kind of funny, but we wanted to kind of normalize across different snowpack samples so that we could plot it on the same figure to make it more easy to look at. And the blue, deuterium? I'm sorry?
That's the deuterium?
It's more of the diagonal offset from principal component analysis. So I'm actually arguing with John Frank about even using this because it makes no sense to isotope hydrologists. But it's the same thing. It's sort of how much is it offset from the meteoric water line. And the red symbols show measurements of the snowpack during, we'll start with the blue, which is in the middle of the winter. And you can see from January, which is blue, to April, which is green, we get a lot of moisture input in the spring as snow, and that builds up the snowpack. That moisture in the spring is a little bit warmer, and so it has an isotope ratio value that's different from that comes in the winter. And then if you go through the ablation period during snowmelt and loss, note that the pattern with depth remains the same. What really appears to be happening from April, which is green, to red, which is June, is just the peeling off of the surface layer. And without advective mixing within the snowpack, you're not going to have a net isotope effect on the remaining snowpack if everything is getting lost from the surface in the system. So even though 50% of the water that's input into this mountainous system gets lost as sublimation, at least at this site, maybe not the site Elise worked at, but at least at this site, has no isotopic deuterium excess effect. It's not falling off the meteoric water line, and so we have difficulty assessing the influence of that on the isotopes of the snowpack. And thus it's missing then, that effect is missing from the integrated signal that's moving into the lakes. if you want to use lakes as an integrator of these processes. Okay, I'll go quickly. I just have a few more slides. Ended up in right about the hour. We're looking at this at a spatial scale because we noted the strong kinetic isotope effects of sublimation from the Biedermann study, which was done at lower elevation, and the lack of that at our higher elevation sites in the mixed conifer forests, right at about 9,500 feet elevation from the previous slide. So apparently at some sites, the sublimation evaporation of the snowpack has a strong net isotope effect of the residual snowpack, and other sites it doesn't. So it's likely that the sublimation processes and the advective metamorphosis of the snowpack is different across those sites, which is important if you want to model the evolution of the snowpack and its melt dynamics and its evaporation dynamics over the course of the year. So a previous student of mine who's now here at the University of Utah did a study where he collected snowpack samples from across an entire watershed and classified the vegetation into these various components, but the ones to pay attention to are the green conifer, kind of in the middle of that symbol diagram there, the red conifer and the gray conifer. The green conifer are trees that have not been attacked by bark beetles. The red conifer are trees that have been recently attacked, but the dead red leaves, the needles, are still sitting on the tree. And the gray conifer are trees that have been dead maybe for a couple of years, and all the needles have fallen off, which we think leads to a very significant impact on the surface water and energy budgets. So that's just an example of a clip out from some of the spatial classification, land cover classifications that he's using across this entire watershed. And what he did was then to collect snowpack samples from a variety of sites, including across all of these different land cover classifications, as well as across elevation gradients, because we know that the elevation can be an important factor controlling the energy balance, the snow metamorphosis, and potentially also the input isotope ratios of the snow. So a lot of samples of snow, our Picaro system's going crazy, making measurements, and this is just showing the elevation model on the right. The top left is the high elevation zone. The bottom of the drainage is to the bottom right. And then the land cover classification for that watershed on the left. You can note there's quite a few lakes, subalpine lakes, snow-fed lakes up at the top of the watershed to the top left. But maybe you can't see it from this distance, but especially at lower elevation, there's a lot of gray trees that have been killed by bark beetles. And so Evan modeled the variability, the spatial variability, in the dxs value of the snowpack using those parameters, the land cover, the elevation. And he found two things to be significant in the modeling. And here I'm showing something called line condition excess. It's just like deuterium excess, but it's just accounting for the local meteoric waterline, which might not have a slope of 8. So it's the offset of the local meteoric waterline rather than sort of this global equilibrium value of 8. In this case, it doesn't matter if you use the normal dxs or this sort of local line condition excess. It's the same thing because the slope of our input is right about 8 anyway. But what he noticed is that elevation and percent of dead trees without leaves strongly influence the deuterium excess value of the snowpack, such that at lower elevation and with dead trees, the dxs value was quite a bit lower than in other conditions. And he produced a spatial map of that dxs value. So notice at the lower elevations on the bottom right, you have a much lower dxs value reflecting probably the influence of the sublimation effect. But even though there's quite a bit of sublimation from the high altitude areas to the top left, we're not seeing that even under dead trees, probably because the process of sublimation and the conditions under which sublimation and ablation occur are much colder and lead to this sort of peeling off of layers rather than at lower elevations, you're probably getting more of a melt and mixing process leading to the capturing of that sublimation kinetic isotope effect in the snowpack. So that's interesting stuff, but what this also does is allow us to fingerprint sources of water in the watershed. using this dxs value. The runoff that's occurring from low elevations is going to carry a different isotope fingerprint than runoff occurring from higher elevations because of these interesting snowpack dynamics. And there are a few ideas about why we're seeing what we're seeing. I'm not going to go through those. And one last couple of slides that I want to show you from John Frank's work. John is finishing up his PhD with Brent Ewers in my department of botany at Wyoming. And he's also the manager of the Ameriflux eddy covariance flux site at the top of the Snowy Range, just west of Laramie. It has a long record of CO2 and energy and water fluxes from the system. And John has been monitoring sublimation in the winter using this eddy covariance system. And he was able to capture, because of this long-term measurement regime, was able to capture the sublimation, the cumulative sublimation over the winter in this forest before the outbreak of the beetles and then after the trees had undergone quite a bit of mortality, at least some of the trees in the system. And what he notes is that the sublimation has declined with this bark beetle disturbance and mortality within the forest. It's declined. And if you're just thinking about the snowpack on the ground, that doesn't really make sense, because you can think, okay, well, there's snowpack on the ground, you're killing the trees, there's going to be more radiation, that's going to drive more sublimation. But the argument here is that with a living canopy, with a full needles, you trap a lot of the snow in the canopy, and then that's what's sublimating to the atmosphere. And with lack of trapping of that snow in the canopy, so it's like an interception of liquid snow, but this is interception of liquid rain. This is interception of snow in the canopy. And the death of those trees, it's likely leading to reduced sublimation with disturbance of this forest. And these are some pictures of one of these snowfall events, starting from the top left and moving to the right and then to the bottom panels. Shows you how much snow can be captured in the canopies and how quickly it can sublimate right back to the atmosphere. So this is a very dynamic system. And you can imagine with a bunch of dead trees, the snow is going to fall right to the floor and the snowpack on the ground and be less subject to this rapid sublimation effect. And John is, and I don't have any data to show yet, but John, for his dissertation work, the last chapter of his really nice dissertation, and I'm on his committee, he's developing a dual source flux model to characterize the sublimation from the snow and from the canopy. And because we have now an optical laser system to measure the water vapor isotopes in the profile in this canopy, we're also John will also be able to model the isotope fluxes, hopefully capturing a signal in the isotopes of sublimation that can help to verify the energy and water flux model that he's developing. Some very, very creative work that's happening. And here's just a picture of us setting up the water vapor isotope analyzer. And you can see the different roles for the master's and PhD students there. And these are just some examples of the kind of data, the continuous data that we're capturing. I don't have any real analysis to show you yet, but just to show you that we're capturing some really interesting signals in this water vapor isotope profile in this forest system. Remember, this is 9,500 feet, and the winters are really cold. And you can see the water isotope ratio values in the warm season go up, as you would expect, because of the continental distillation effect. And in the wintertime, the air gets really cold and dry, and the water vapor isotopes get low. And there are some interesting periods when the samples that we're measuring at different heights begin to diverge. And John gave me this slide just a couple days ago to show to you. It's kind of complicated because he's developing it for a paper. But take a look at the bottom two left panels. Those are the oxygen and hydrogen isotope ratio values of water vapor in the profile of the canopy during this wintertime event. And yes, November is winter in Wyoming. We've got snow. And you can see that there are time periods, like particularly later in the week and maybe a little bit earlier in that period, that the isotope ratio value of the vapor in the canopy diverges between the heights. For the most part, it's a very well-mixed system. The turbulence is really high. It's one of the most turbulent and windy eddy flux sites in North America. But there are conditions when the isotope ratios diverge between the different heights, and those happen to be when we get these snowfall events. And the big delta hydrogen and oxygen isotopes on the right-hand side just show the difference between two paired positions within the profile. The pink is the isotope ratio difference between the snowpack level measurement and the canopy level measurement. And so you can see there are times when that difference between the isotope ratios diverges quite rapidly, particularly on the far right-hand side for both oxygen and hydrogen. And those are the periods when we get the snowpack that falls into the canopy that gets rapidly lost to sublimation, and we get these strong isotope signals within the canopy. So that's the data that John is going to use to compare against his energy balance and flux model to see if we're picking up these processes in this system. Okay, so that's things for the future, but just to give you a taste of where we're headed with all this. And that's it.